And this is what harmonics are doing. Distortion also we have to take into account. So distortion means we earlier had two-dimensional triangle. So with the harmonics, we have a third dimension, which is D, we are calling it. And so it is now true power factor is P square plus Q square plus D square. Earlier it used to be only taken as P square plus Q square. So this distortion also has to be taken into account for calculating the power factor, for calculating the kVAH, the all the parameters have to be as per the distortion also is coming into the picture now. The effect of corporation this harmonics. So there is some disturbance. I think some mic we have to switch off. Okay. So suppose this is taken into account distortion and the meters are calibrated as per that, then the power factor which is being done at some places and wherever it is not there, it is being implemented. So if the power factor, suppose we have a fundamental power factor of 0.996 without taking into account the harmonics, and suppose the harmonic distortion is 5%. So there is not much difference. The distorted power factor is this much and true power factor also is very close to 996. But as we go further, the harmonics keep on increasing. Suppose the worst value, suppose we have a 40% THD value, the 996 remains same, the original displacement power factor, but the true power factor will become 0.925, which if we translate into billing, it will have about 7% extra billing. So this is the amount of change we can have in the billing and in the true power factor when we have harmonics in the system. So this is just one slide which I like to always impress upon the type of capacitors which we are using. So normally earlier people used to have only APP capacitors, and even today many consultants they just keep on recommending APP only, but APP is not a safe capacitor. From the safety point of view, it is not recommended for LT applications, and nowhere in the world people use APP capacitors for low voltage. Everybody is using MPP, self-healing type. It has the self-protections, built-in protections. There is a self-healing mechanism. Suppose there is a inrush current, heavy inrush current for any reason, the metallizing on the film evaporates and the fault is clear, and the capacitor continues to run without any almost negligible change or no change in the capacitance value. So this is the self-protection available within this, which is not there in
recording stopped,
which is not available in others. And then we have this another overpressure interrupter mechanism. Here there are gases generated inside. The pressure is built up whenever we have some higher current for any reason, whether it is fault current or any inrush current or anything. So if this current is exceeding certain limits, or if the capacitor is coming towards the end of its life, then this pressure is sufficient enough to lift this lid and the connection mechanically breaks. So there is no electrical system required to protect. It is mechanically protected. The capacitor is isolated on its own without any external protection. And third thing is this segmentation. The film is segmented. Suppose we have a one continuous film. This is used to enhance the life of the capacitor. Suppose we have a heavy current inside, any inrush current for any reason, and it is one continuous film. Then the fault, if it is bigger fault, the fault spreads throughout the film and the capacitor fails. But if we have segmentation, the fault is restricted to a particular segment, and the capacitor continues to run. Only one segment is isolated. And this is again another feature of particularly phaco-capacitors. There is an end connection. So all end connections are without any soldering, because soldering, when we do, we lose some MFD value. And another advantage of this end ring, this is a contact ring is there towards at the end of the film. Here it is making the you can say construction very robust, and facilitates the operation of this overpressure interrupter mechanism. Is also it helps in operating this protection better. Then we are having some few benefits of power factor correction, which will again just briefly describe. Although most of the people must be aware, the KVA demand is reduced when we are having power factor correction, as we have seen in the second slide. Then the current also is reduced. Suppose we have a power factor of 0.8 and then we go to 20% current is reduced, 20% demand is reduced, and it also reduces the losses. Then the voltage profile of the system is improved. When we are running at a lower power factor, our voltage is poor also, and when we improve the power factor, the voltage profile improves. Then entire system, the transformers, the cables, and everything is utilized to the full optimum design value. We can take the maximum out of the system, and then whatever penalties are there, we can avoid that if we are maintaining the power factor, or the incentives we can avoid. So these were the slides how to improve the power factor, reduce the demand, improve the billing, and all those things through the reactive power compensation. Because even the harmonics are getting built into the tariff structure, so that this also is part of the savings. So then harmonics we have in the systems, because most of the systems today, the loads, they are non-linear. About 70% loads are non-linear, which introduce harmonics into the system. And these harmonics create a lot of issues, which we will come across later in some slides. So non-linear means the voltage and current profile are not following each other. The current is having a non-linearity, and that is how it is represented. And what are the various non-linear loads?
Hello.
The largest non-linear load is
कॅपॅसिटर्स वाला बलदेव नारंग तुम्ही ओळखता का? हा, तो प्रेरणा मधून ते.
So its largest non-linear load is VFDs, variable frequency drives. So they constitute maximum non-linearity in the system. Then we have also DC drives, UPS, thyristor heating, induction furnaces, arc furnaces. Lighting means all lighting is today non-linear, whether it is fluorescent lamp or CFL lamp or LED, everything is non-linear. Then battery chargers, welding controls, rectifiers, SMPS supplies, all these are introducing non-linearity, and they are introducing the harmonics into the system. So this is briefly, we explain how the harmonics impact the working of the system. Suppose this load is there, it is non-linear load. We represent a source, we call it harmonic current source, because of the non-linear load. So this non-linear load is introducing this current, which is being attracted by the capacitors, because capacitors have the minimum impedance for higher frequencies. The harmonics are at frequencies of 250 Hz, 350 Hz and all. So capacitor provides the lowest impedance path to the harmonic. So they are the first item to fail in an harmonic environment. So whenever we find capacitors are failing, means there are harmonics in the system. Then these harmonic currents, they flow back to the system also. They are exported back to the grid through the transformer. So this is the standard normal system when we don't have any improvement done or mitigate the harmonics. And there is another problem. This is not the only thing, that the harmonics which are generated by the loads, they are flowing into the system. There is another phenomenon, because this is capacitor and system impedance. They are in parallel. So at some frequency, they are causing resonance. So if this frequency of resonance is a harmonic frequency, suppose the resonance is occurring at 350 Hz or 250 Hz at fifth harmonic or seventh harmonic, that harmonic gets amplified. Normally we have fifth and seventh harmonic always in the system, and when the resonance is taking place at any one of them, so that harmonic gets amplified. The 10% may become 30%. So it is not only the generated harmonics, it is the amplified harmonics due to resonance, which is also flowing to the capacitor, also going back to the system. So our aim is to mitigate this initial harmonics as well as to avoid the resonance condition. So what we do is we are putting a reactor in series with the capacitor, and we are tuning the reactor normally at a frequency close to the fifth harmonic. The most common frequency is 189 Hz, 7% reactor. Means 100 kVR capacitor means 7 kVR reactor. So this is what it is doing is it is doing 2-3 jobs. One is that it is providing low impedance path to the harmonic, fifth harmonic, and that is being absorbed here. Part of the harmonic is absorbed here, not completely, because we are not having a fully tuned filter. It is detuned. It is at 189 Hz or maybe at 210 Hz. And the second is this reactor is also reducing the inrush current. Capacitor is a short circuit when it is started, switching on. So the current could be 150, 200 times. So this reactor is reducing the inrush current. The capacitor life is in decrease, life is improved, and the system also is not stressed with that inrush current. And the third, the major requirement of this reactor is that it shifts the resonance point. Suppose the resonance was taking place at fifth harmonic or seventh harmonic, so it is shifted to a safe place, maybe between third and fourth or second or third. And so it is doing all these jobs, avoiding the resonance, filtering some of the harmonics, and also reducing the inrush current. So this reactor is very, very crucial. So today, no capacitors are used without reactors because all the systems have harmonics. Everywhere there is a risk. So we have to mitigate that risk and we have to use capacitors with the reactors. And plain capacitors are almost prohibited today. Nobody uses them. And the capacitors, when we are connecting with reactor like this, there is a voltage rise across the capacitor. Suppose there is a 7% reactor, the voltage will increase around the capacitor, across the capacitor by 7%. And suppose there is a 10% tolerance also. So what we do is the 440 volt system, we use 525 volt design capacitors, otherwise they will fail. So this is how we control the harmonics at the, you can say, power factor control system itself. Whenever we are using power factor APFC panels, we are using it along with the reactors and we are mitigating some of the harmonics as well as we are also avoiding the resonance conditions, and the export of harmonics to the grid is reduced. So harmonics could be even numbered, odd numbered. Evens are not a problem because they cancel themselves in the first half and second half. Odd number mainly they are very crucial, third, fifth, and seventh. Out of this, third again is also very critical because it is generated by single phase loads. Whenever we have single phase load, large proportion of single phase loads, like in IT industries or hospitals, multiplexes, and all commercial buildings. So there the third harmonic is generated. So that third harmonic is a zero sequence harmonic. It flows through the neutral. So the neutral is overloaded. What we do is in IT sector particularly, we use 5-core cables because the neutral current could be even 2 times the phase current. So if the normal half-core neutral is there, it will burn out and there could be accidents and fires and all. Hazards are there. So for installations where there is a single phase load concentration is more, we use 5-core cables. I'll just take a call. Hello. हेलो हेलो हाँ विनीत सर, मैं आपको थोड़ी देर में फोन करूँ क्या? 1 घंटा और लगेगा, मैं एक वेबिनार ले रहा हूँ. So fifth and seventh harmonics, they are again positive sequence and negative sequence harmonics are there. So all harmonics they create overheating, whether it is third, fifth, or seventh. And some of the common problems are there, which we'll discuss in the next slides. But third, as I told more particularly, single phase loads, there we have to strengthen the neutral. Besides other measures like harmonic mitigation through filters. So this is how the system looks like. This is third harmonic is shown in the diagram along with the fundamental current. So it has three cycles in one cycle. And the net harmonic profile looks like this dotted line. Here we have shown third harmonic and fifth harmonic, and the net current is also shown. So this is how it gets distorted. Then the harmonics, when they are generated by the loads only. And loads, maybe from low voltage itself, we start generating the harmonics, and these harmonics flow towards the bus. Like at PCC loads, they will flow towards the PCC bus, and there they will get converted to voltage harmonics. Again, from PCC, they go to the transformer towards the MV side, and then again towards the HV side through transformers, and finally to the grid. So the current harmonics flow from low voltage to the high voltage, and they get finally exported to the grid. And at each voltage level, they are getting converted to voltage distortion, which is we call it voltage harmonics. So at all these buses, voltage harmonics, they affect all the loads connected to that bus. Whether they are linear or non-linear, everything is affected. And from grid itself, whatever voltage distortion is there, it flows back towards the low voltage. So this is the flow. Current is from low to high, and voltage harmonics are from high voltage to low voltage side. So there are some common impacts of the harmonics, the bad effects or the adverse effects of harmonics. The heating is there, increased heating due to iron and copper losses, and performance characteristics of each and every system or load changes because all the systems we design for 50 hertz, and when we are having these harmonic currents at 250, 350 and all also flowing along with the fundamental, now we don't get the characteristics for which we design the system, so there is a distortion. Then overloading of neutral occurs for third harmonic, as we have discussed earlier. Then one of the first symptom of a harmonic presence is capacitor failures. And then there is a spurious stripping of thermal protections. Suppose we have overload protections in the breakers or thermal relays, bimetal relays and all. They sense harmonic current also as a normal current, and they trip prematurely without any overloading. They also trip. So we find spurious trippings happening because of the harmonics. Then the controls, similarly like loads also, the controls also get affected because they are also not getting pure 50 hertz supply. They are getting erratic harmonics are there, and their operation also can be erratic. Then the communication is affected. So there is an interference with communication, and the meters, they don't read correctly. Many times we have seen even the meters stop reading when the harmonic concentration is very high. So this is to show the most dangerous aspect of harmonics. Suppose the harmonics are there and we are not taking care, and there is a resonance condition taking place, the harmonics could be getting multiplied like anything, and there could be a final outcome like a major accident or a fire. Then we have the IEEE 519 guidelines. Most of us, we are at this 1 kV to 69 kV, most of the consumers. So the voltage harmonic distortion is THD is 5%, and individual harmonic level is 3%. And the current distortion, again, most we are at this 20 to 50 ISC by IL ratio, because we have to see the TDD value. Here we don't see the THD value because THD does not represent the severity of the harmonics, because the system could be not loaded to full extent, and even 100% THD could be a normal thing for a system which is not loaded fully. So we have to see the TDD value at the full load current, how much is the harmonic, that we have to see close to full load current, and that is TDD and THD tend to be equal at that time. So between 20 and 50, we are most of the time available there, most of the consumers. So TDD 8% is the requirement normally. Then this is how the harmonic distortion is calculated. Formula is there. Fundamental we leave aside, and I2 to up to whatever harmonics we have, we multiply by 100 and take the ratio with fundamental current. Then we call it THD. And when we take this ratio with the load current, maximum load current, then we call it TDD. So these are some formulae, and this is what voltage I said. We have the voltage rise across the capacitors when we connect the reactor. So it is normal voltage multiplied by 100 by 100 minus P. P is suppose 7% reactor. So this is how we calculate it. So for a 7% reactor, if we are having, which is most common, the capacitor should be above 473 volt. Normally we use 525 volt. So then we have to mitigate these harmonics. So there could be detuned filters or tuned filter, and then we have special purpose transformers or active filters. Filters we have already explained. We connect the reactor, and the reactor is tuned to that frequency which we want to filter out, and that is how we absorb some of the harmonics in this reactor capacitor combination, and it is not allowed to go back to the grid. And that means what we do is we provide a easier path for the harmonic to be absorbed through this combination, so that it is not transferred to the grid. Then we have the active filter. When we tune means if we are fully tuned 100%, suppose we tune it at 250 hertz, that we are trying to pass almost all the current, harmonic current, through the filter. But then we have special purpose tune filter. Tune filter means we have a different principle in this thing. In active filter, first I'll take the active filter. Active filter means like in this, we are giving a low impedance path to the harmonics. Here we are generating harmonics which are 180 degree out of phase with the fundamental, with the harmonic current, and we are injecting into the system, and we are killing those harmonics. So there are, the principle is that here we allow it to pass through a designed circuit, and here we are cancelling the harmonics. So both are effective in their own manners, and there are advantages, disadvantages, and we have to use sometimes hybrid systems also. Many times we can manage with just passive filters, just where we are using only reactors. And sometimes the harmonic concentration may be very diverse. It could have many harmonics. The load may be very difficult loads. So we have to use, along with passive filters, active filters also. So active filters, we can generate any harmonic current and cancel out the present harmonics by injecting it at 180 degree out of phase. So we have to only configure the harmonics in the system. So this is how I was explaining. When we are connecting a reactor, what we do is, this is a curve between harmonic frequency and the impedance of the system. So as we go along, harmonics are increasing. So what is happening is the impedance of the system is increasing initially, and then it attains a maximum value and it starts decreasing. What happens is, at this maximum value, this is the point of resonance. So this should not be at the point where some harmonic is present. So here it is close to 7th harmonic, 7th frequency is there. So if we have a system like this, just capacitor is there. This is only capacitor, plain capacitor we are connecting. So this will cause a resonance at 7th harmonic, and the 7th harmonic will be amplified. So what we do is we connect the reactor. So when we connect the reactor, this point is shifted to a safe place. Either it is here, or it is here between 3rd and 4th, or maybe at 4th, or between 2nd and 3rd. And this the resonance is avoided, and it is system becomes safe. And here we have shown two lines yellow. Means suppose we are having two systems. Suppose one system we have tuned to 5th harmonic, one is we have tuned to 7th harmonic. So we'll have two resonance points, but both are safe. One is at 6th, one is at 4th. So there is no resonance condition. So this is the advantage of having a reactor. So when we are having two, means we are trying to filter out more harmonics. We are having a full filtration sort of effect we want. And otherwise we are connecting partial filters. 7% suppose we have, it is hardly any mitigation is taking place because it is too far away from the 5th harmonic. But if we take it closer, like 210, 235, we get a better filtration. So these are different combination of reactors shown here. And here again, the harmonics, when we are having a plain capacitor, the distortion is maximum voltage distortion due to harmonics. And when we are using a 7% reactor, maybe it is reducing to some extent. When we are using a better tuned reactor, it is reducing further. The distortion is further reduced. And for full filtration, suppose we are able to achieve, there is hardly any distortion. At 7th harmonic, the distortion was there, so that we have controlled here. So this is how we calculate the tuning frequencies. It is 1 upon 2 pi root LC. This is we can how we have calculated. We have shown the formula is also something. And suppose the resonance also, there is a empirical formula. We can find out where it takes place. Suppose we have a short circuit MV of the system, and we have some MV AR capacitors connected. If we divide these two and take a square root, it will show where the resonance is taking place. Suppose we have a 1000 MVA short circuit level and 20 MV AR capacitors are connected, then the resonance will take place at 7th harmonic. So in this, what we do is, without doing any harmonic mitigation measures, because that may take time, we can simply either add some capacitors or take out some capacitors so that this resonance is shifted. So this is how they have calculated the tuning frequency. Means for 7% it is Fn divided by 0.07 square root. So it comes to 189 Hertz when we have 7% reactor. This is again voltage same I have shown earlier also. And then if we have a close to 6%, 5.67%, 210 Hertz or something tuning, then the voltage is 466 volt itself. Here it was 473 volt. So in any case, we are still using 525 volt only. So this is how we are calculating the tuning frequency for different percentage reactor values. For third harmonics, we use 14% reactor. Means 133 Hertz we are tuning. So it will filter out third harmonic. So this power system impedance have already explained. Initially it is increasing and then it attains maximum value and then starts decreasing. So here the initial curve is inductive, this side, and inductance is determining the frequency impedance. But this part, the capacitor becomes a major item. This determines the value at higher frequencies. So this active filter I have already touched up earlier. So what happens is we are generating harmonics here, and we are generating at 180 out of phase and cancelling them. But this active filter can do many other jobs. It can generate reactive power. Suppose we generate 50 hertz current, then we can use it as a capacitor or an inductor. And then this can be used for controlling the unbalance. It can be also used for controlling the voltage variations, dips, voltage dips and sags, and then oscillations, flicker. So all these things can be controlled by the active filter. When we are using it as a reactive power source, we call it STATCOM or SVG, static var generator. But the construction is same. Only thing is utilization is different. So this is how active filter. We are injecting the current. This is the load current. This is the compensation current generated, and this is how the final will become sinusoidal. So this is just simple about active filter advantages, which I have already explained slightly, some of them. Then there is another phenomenon in this active filter, which will be more useful when we go to renewable frequencies, harmonics in renewable systems. So as we go higher, initially fifth and seventh harmonics we can filter out easily, but as we go higher, there is a derating of the system. So whatever, suppose 100 ampere system, we don't get 100 ampere, we get maybe 60 ampere or 40 ampere at higher frequencies, and ultimately it doesn't work beyond a certain frequency. Particularly, normally we are comfortable up to maybe maximum sometimes 17th, 19th, or in some cases maybe 23rd frequency, but beyond that it doesn't work. So there we have to go back to again passive filters, high pass filters we call them. So that we will discuss in renewable when we come to that. So here again, the system could be closed loop or open loop. We can have the signal taken from either way. And then we have this thing, sensorless control also, means voltage itself is a signal, and we can control voltage harmonics with this sensorless control. So this kVH tariff I had talked earlier. So what is happening is earlier kWh billing used to be there, and with the kVH, we have to maintain unity power factor round the clock to get the maximum advantage. Earlier it was an average power factor, maybe over a month average, suppose we are able to maintain 995 or something, we get the full incentive. But here, unless we are continuously maintaining unity power factor, there is some incentive lost. So this is explained here. So here the power factor over a period of almost 1 year is very good. It is 97, 98, 95, or maybe in that range 99 also. But it is between the kWh and kVh difference is there, and the difference, the billing, about 7 point at the rate we have taken the tariff. So about 85 lakhs per year extra was paid by this consumer because the power factor was not continuously being maintained. So now we come to this renewable. Renewable, because there is large scale induction today. We have about 1679 gigawatt of renewable power today, and that we have to take it to 500 gigawatt by 2030. So maybe annual addition is 44 gigawatt. It is a very massive addition, and globally also the same. It has to be 3 times whatever we have the capacity today. It has to become 3 times by 2030. So globally we have to add about 1000 gigawatt every year, and as on today it is about 3500 gigawatt. So India is the fourth largest renewable market globally, and still the dependence remains on thermal power. But where the problem is because of the emission density, intensity is there, so we are changing over to renewable. And per capita emission have written 1.7 tons of CO2 is 60% lower than the global average of 4.4 tons per capita emission. So India stands at a better footing compared to the international emissions today. And when we are having this addition, so there is a problem of grid stability. All these renewable plant, grid scale renewable plants, uh, they are coming in the range of maybe 500 megawatt, 1000 megawatt, and all gigawatts in scale. Now they are coming. So they have their own reactive power requirements. Initially, the plants came without any reactive support. The plants were added, but there was no reactive power support provided within the plant. So then they made it compulsory that at least 33% reactive power is also required when you are commissioning a wind plant or a solar plant. Say 1000 megawatt means 330 MVR. You have to have this reactive power support within the plant itself. 33% is the requirement today for adding the renewable plant to the grid. So what is happening is initially it was only switched capacitor banks which were added to the system. But again, these plants are coming at remote locations, like in Rajasthan, where the grid is very weak. The grid inertia is not there because there is no thermal plant nearby. It's only renewable plants coming there. And the short circuit ratio is also very poor in the range of 5 to 10. And what is happening is whenever there is a fault, the inertia is not there, the fault is not cleared in time, and the grid collapses. And there was a generation loss about 1000 megawatt in 2022 over a year period. And there were about 28 instances of this loss. So after that, the CA mandated that we have to have STATCOM, the dynamic reactive support for taking care of low voltage right through and high voltage right through conditions. These occur during particularly fault conditions, and this was alone also not sufficient because we have to see that even if we have a STATCOM, but if we don't improve the inertia, if we don't take care of the short circuit values also, or maybe at this short circuit value also, if we have a good inertia and we are able to clear the fault in time, maybe we can manage with STATCOM. So the grid inertia, we are having all these additions with inverters which are grid following inverters. They don't have any battery capacity. They are only grid following, and we need grid forming inverters, means with voltage with a battery backup. So then only the inertia will be there in the system. So now many tenders, they are coming with the battery backup only. So this is, as we go along, we have to see that we are not having a weak grid, and we have ultimate aim to go 100% renewable. So all these challenges have to be taken care, and this is what like STATCOMs have been taken into account. The grid inertia also, either we have to have these synchronous condensers in the system, or we have to have battery backup. Then only this can be increased. And another problem what we have in these harmonics generation by the renewable plants, they generate very typical harmonics. It is not a standard harmonic like fifth and seventh we normally have in load six pulse converter. So they generate fifth harmonic and seventh harmonic normally. Single phase load, they generate third harmonic. But in renewable plants, we have harmonics in the range of maybe 23rd harmonic, 37th, 49th, and all. And these harmonics, they cannot be controlled by active filters, they cannot be controlled by STATCOM, and they cannot be controlled by standard passive filters, LC tuned filters, detuned filters. So here we have to have a high pass filter where we use another element called a resistor. So that resistor is connected in a way that it absorbs all the higher order harmonics, and it is uh, mitigated through the resistors basically. So those high pass filters are designed for mitigating these harmonics generated by renewable plants. And the one good thing what has been done by CEA is that they have mandated that all these plants, whether they are existing plants or they are incoming plants, they have to meet the IEEE 519 norms of harmonics. So almost every plant, whether it is existing or incoming, they are coming up with the high pass filters now. And this is what we are also into very much in this area. We are supplying this dynamic reactive power support. As I told, we are shifting mainly towards renewable. So this is our major now uh, source of you can say business, STATCOMs. We have a collaboration with uh, one of the largest manufacturer of STATCOM in the world today, and we are importing and we are supplying this STATCOM. It is not only for renewables, but we have started supplying these STATCOMs to the industrial also, because this is a replacement for the standard capacitor, switch capacitor banks, and it gives uh, support inductive as well as capacitive. So both ways it is able to control. And industrial also, because there is a kVh billing, and when they are using normal capacitor banks, the effect is not that accurate. And particularly even the cost wise also, these STATCOMs are now becoming very competitive. They are getting almost as competitive as the capacitor banks. And that is why there is a shift from the switch capacitor banks. And this is one area where we are supplying. And the second one is high pass filters also we are manufacturing, and we are giving it to all these renewable plants. So grid forming inverters, I was telling, we have to have synchronous condensers or battery backup. And then harmonic mitigation, we, as I discussed, we are having high pass filters today. Then another problem is these systems, when they are being manufactured, or they are before they are actually taken into line, there is a system modeling done. That modeling is approved by the CEA or the grid integrating agencies, and they have to satisfy the grid code. And after connection, it is physically also checked, and then we see that the systems are safe and they are not affecting the grid stability. Similar in the modeling, we have to do the inverter selection has to be very proper. The tuning has to be proper. Otherwise, it goes into maybe oscillatory mode, and it trips before the faults or things are cleared and all. And this is power plant controller we have in that. There again, these sees when there is a fault. So we have to clear the fault in time so that there is no interruption in the system. So this STATCOM listed out some point. This is grid stability we are enhancing. It provides dynamic support for voltage, inductive or capacitive both. It can also mitigate flicker. It can mitigate harmonics up to 23rd harmonic what we are supplying. Mostly the STATCOMs, they mitigate up to 13th harmonic, but what we are supplying, it can mitigate up to 23rd harmonic. The support is available in both inductive and capacitive directions. It's a very low power loss item. Less than 1% is the self consumption. The response time is less than 5 milliseconds, so that there is no interruption in supply. Voltage flickers we can control. Operating range is wider. Harmonics can be suppressed. The design is modular. We can increase easily, upgrade the systems, and it is compatible with the renewable systems, and as well as industries also we are giving now. So this is how it looks like. This is a container which has the uh, IGBT based inverter basically. It is like an active filter system only. And this is the incoming. We have the connections from the grid. And this is part of the system, the reactors for PWM operation. It is there. This is how it looks like. And the field, it is like this. This is the container STATCOM. These are the reactor part of the system. Then the cooling system, it is water cooled system. And if the grid connection is there. So this is water cooling is shown. So this is again also I have earlier told 2030 will one third of the global electricity will be there. And then this rapid increase is driven by continuous technological advancement, falling costs and supportive policy network framework. A lot of incentives are coming from the government today. And net zero we have to achieve by 2050. The global warming target is 1.5 degrees centigrade. Then again, it has to be linked with the clean hydrogen because these renewable, when we generate, we can generate hydrogen through that also when it is not required for loads, and that can be stored.